All right, guys, welcome back. So I think we can get started. I can still see some people coming in as I talk, but let's just get started. So last time what we've done was to take a look at some conceptual implementation of the distributed optimization and some of the algebraic tricks uh, to reduce the computational cost for computing linear regressions. So if you recall, we talk about the pseudo inverse, right, which involved the computation of the x transpose x inverse times x transpose y, where x is the feature matrix and then y is a vector containing the response variables, right? So we compare two different strategy. One is a naive implementation where you just multiply everything in the order of appearance from left to right. And then the other strategy was to, just apply a simple, algebraic trick of, doing the computation in an order that can minimize the computational complexity of the entire process. And then we kind of move on to the implementation, the NumPy version implementation of distributed gradient descent algorithm, which could be used to find the solution for a linear regression problem. But in a way that we can distribute the gradients across different computational nodes and then let the computation happen over there. And then, towards the end of the, class last time, we talk a little bit about how things can be done in Spark. At the end of the day, all the heavy lifting, all the distributed optimization and everything is going to be taken care of by Spark. And as a data scientist, as a user, you don't really, need to care too much about those, what's happening under the hood. So that was kind of a sneak peek that I gave you last time at the end of the class. So today we're actually going deeper into that, and then I'm gonna explain some core concepts regarding the machine learning library in Spark. So as I put up here while I was speaking, you need to configure Spark on Google Colab environment. So you better go to the icon page where you can copy and paste this configuration code, and once you're done with that, then please go ahead and run this cell so that we are ready to get started. Okay, and if you're done already, here's another thing I want you to do, which is to search for UCI machine learning repository. Go visit there, and then there are some data sets that are most popular since 2007, and one of them is called a wine data set. Okay, so go ahead and click on that, and then if you look at the data folder here, you will see wine.data. Okay, well, actually, sorry, not this one. Let's use a different wine data set, which can be searched by wine quality. Oops, yeah. So wine quality data set, UCI machine learning repository. So that's a slightly different data set. Okay, not the same as the wine data set. So go ahead and look for wine quality data set. And then if you go to the data folder, then you're going to see two CSV files. Okay. Yeah, if you happen to have already opened the lab material, you can simply just run the cell over there directly. But if you want to just follow what I'm doing from the scratch, then you probably want to actually go ahead and search for the UCI lab machine learning repository, and then manually find this wine quality data set. So if you're having a hard time finding the data set, then the URL is not too long. So maybe you want to just type that in directly in your web browser. Okay, so I'm going to give you a few more seconds to do that. So two things. One is to configure Spark on Colab, and then the second thing is to search for wine quality data set. Now, what we're going to do then is to right click, and maybe let's use the red wine data set. Well, it doesn't really matter, but yeah. And then click copy link address. So in that way, you can copy the URL of that. And for convenience, I will paste that in the chat window. Why did I not realize I could actually copy and paste the URL in the chat window? So wget is a command to download a file from URL. And then the URL to that CSV file is like this. You can find that on the chat window. And run this. We'll download wine quality-red.csv file, download it on your Colab machine. Okay. Now, after that, you know the drill, right? So from PySpark, let me scroll up a little bit so that it's easier to see. PySpark.SQL, import Spark session. And then I'm going to create a new Spark session called Spark, which is Spark session.builder.app name. And then let's call it wine quality. And then get or create. Okay, so you know the drill. So once you have created a Spark session, then the next thing is obviously to read the CSV file, which I'm going to just use the spark.read.csv. And then the file name is wine quality-red.csv. So just copy and paste. The CSV file comes with the header. And interestingly, the CSV file uses semicolon as a separator. So I think I mentioned this when we were talking about the data frame. So usually CSV file, I mean, by definition, it's a comma separated values. So usually comma is the symbol to separate those values. But interestingly, there's one quality data set, they use colon as a separator. So in that case, you can use this option, sep, and then specify semicolon as a separator. And of course, we're going to need to infer schema automatically. And just to check if the data set is loaded without a problem, I'm going to display the first 20 rows of the data frame. So I'm pretty sure you guys have no problem so far because it's been, you know, in homework problem, right? So, but as you can see over here, the data set looks like this. It contains different traits regarding a wine. And then, you know, for each of the row, we have the information about different wine products. So we have the acidity. I don't exactly know what the fixed acidity and the volatile acidity means because I'm not a wine expert. I'm more of a beer kind of a guy. But you can see, you know, the contents of sugar, the chloride, sulfur dioxide, density of a wine, the pH number. I guess that's another acidity measure. And then sulfates, contents, alcohol. And then at the end, we have the quality column. Okay. So basically, your goal is to measure those traits from a wine product, and then to predict the quality of that wine, okay, based off of the alcohol contents, sulfate contents, the acidity level, density, and, you know, sulfur dioxide contents, and, you know, so on and so forth. You want to predict the quality of a wine. What a fun problem, right? So in order to do that, okay, I'm going to close this results output just to show you more code lines. So what I'm going to do with this is I'm going to train a linear regression model, okay? And for that, the first thing I want to do is to create a feature vector from the columns that are present in the data frame. So actually it was not a good idea to close down that, you know, output section. Maybe I'm going to just, you know, print out only 3 rows. Okay, so that's better. So we have different columns, okay, and then we need to construct a feature vector out of these different columns. And then for this exercise, I'm going to be just, you know, simple, okay? I'm going to use all the columns other than quality to construct a feature vector, which is the regressor. And then the quality values are going to be the response variable in my linear regression model. Okay, so if you recall, df.columns was a command that you can use to, list all the column names, right? That was one of the first lab sections, right? And from here, all the way up to alcohol contents is going to be the input to the linear regression model, and then quality is going to be the output, okay, of the linear regression model. So what I'm going to do is then to select, okay, all the way to the first contents from the end, okay, I'm counting from 0, so that's actually a second one, right? So df.columns colon -1 is a Python, syntax of selecting the list elements all the way through the end except for the last one, okay? And that's going to be the input columns, okay? And these are the features, okay, that I'm going to use to predict the quality, okay? So as you can see, I mean, this is kind of an obvious thing, but as you can see, the features variable contain all columns all the way up to alcohol except for quality, okay? Now, what I'm going to do is going to create a new column in the data frame that contains a feature vector, okay? And in order to do that, without much explanation, I'm gonna import from pyspark.ml.feature module what is called a vector assembler, okay? And as the name indicates, this is a helper function that helps you to create a feature vector by assembling different columns. So how to use it? Well, I'm going to create an object called assembler, and that's going to be my vector assembler. And the input columns to generate a vector is going to be what's stored in features, or to be more explicit, you can actually just go with this, but it doesn't really matter. And then as a result of creating a feature vector, I'm going to create a new column called features, okay? And here, what I'm going to do is to create a vectorized data frame, and that vectorized data frame is going to be created as a result of transforming the original data frame. So after that, let's try to display 3 rows of the vectorized data frame. So as you can see, the vectorized data frame, dfvec, is almost the same, except that here we added this new column called features. You see that? And the features column contains vectors, you can see. And then the elements of the vectors are exactly just these numbers over here. So I just created a new column that contains essentially a vector summarizing all the values on the left, except for quality, okay? And of course, I don't need then, after creating the feature vector, I don't actually need the other columns. So maybe I can make it a little more succinct and select only the features column and the quality column, okay? So in that way, I can actually make it more succinct, so it's easier to view, right? And that's in fact all I needed to do to solve a linear regression problem, okay? I just created a column that contains a feature vector, which is basically just an aggregation of all the other columns. And then I have a column that contains quality, which is going to be the response variable. And from that, here I create a linear regression problem. So from pyspark.ml.regression. So ML is a machine learning module in PySpark that contains all different kinds of machine learning algorithms. And then they have categorized things into regression problems and classification problems. And there are other couple different types of problems. And today we're going to use regression, and especially we're going to use linear regression. Okay. So I'm going to load it up, and then what I'm going to do is define a linear regression problem by specifying features column, and that's this column over here. So I'm going to just copy and paste the column name, and then the label column. So that's the response variable column, and that's precisely this quality column over here. So I'm going to just put that in. Okay. So that's how I define a linear regression problem. And after that, I'm going to train a model by calling lr.fit. So lr is kind of, an alias for that linear regression model that I just created. And then as a result of fitting the data frame, you're going to have a linear regression model. So let's run that, and nothing is going to show up if everything was successful. Now, after that, what this LR model contains is the result of fitting a linear regression model to the given data frame. So the result of that is a set of coefficients, which basically is our variable W that we saw from the previous example. So in our convention, W was the coefficient. And that's a dense vector, which contains these values. So this is W that we obtained from, solving the linear regression problem. Okay. And LR model dot intercept is basically the intercept, literally the intercept, which is the variable B, the parameter B in our formulation. And that's 21.965 something. So it's pretty simple. Okay. Of course, other than coefficients and intercept, you can also display the some other summary statistics. So for example, LR_model.summary will return a training summary. So I'm just going to call it sum. So it's going to return a summary object. And in the summary object, we can see things like, for example, root mean squared error. And maybe I can just print that. And let's give it a label. Okay. We can also print mean squared error, so without square root. So that's going to be mean squared error. We can also print MAE, mean absolute error, which is mean absolute error. So these are the summary of the training, and that's available in this model.summary object. What else? You can have pretty much everything that you can imagine. So for example, R squared is another performance metric for regression models, right? So that's available under that model.summary object with the name of R2. And then there can also be an adjusted R square, if you know what that means. What else? You can also print the p-values, and that's under sum.p-values. So you can go ahead and print them. And as you can see, we have the R square, adjusted R square, and then the p-value. Okay. So it seems like the correlation is not that strong. Okay. Although there do exist some positive correlation, right? It's not that strong. But it seems like there are some variables that, from which you can infer what the quality is, right? So it seems like the third from the last is a parameter, which I forgot what it was. I think that was 1, 2, 3, the pH level. Okay, so the pH level seems to be a factor that has some correlation with the quality of the wine. This is another variable that seems to have some correlation in this one as well. So by looking at the p-values, you can kind of, get a good glance of what it looks like, right? So all of these are available in PySpark, which is kind of nice, right? And if you want to know more about, what's available in there, of course, my recommendation is to visit PySpark documentation. So there are many different versions, but you can just click any of them. My trick is to switch the version number with latest, then it's going to direct you to the latest version of documentation. And then if you go there, then, just search for linear regression model. Then you'll find the section that, oh, this is actually a source code. You can go to the documentation and then here, ML regression module, right? And then over here, you can find the linear regression model. And then somewhere, there's got to be a section for linear regression. There you go. So here's the documentation. Here's an exhaustive list of all the functions and variables that's available in PySpark. So you can kind of scroll down and skim over what's available over there. A lot of it will make sense if you have necessary statistical background. So here, actually, that was what I was looking for, not the model, but the summary. So linear regression summary object over here has a property called the coefficient standard errors. So this is a standard error for each of the coefficient values. We have degrees of freedom, we have residuals, explained variance, features column is something we already know, label column as well. We saw mean absolute error, mean square error already. P-values, we saw that. R square, adjusted R square, residuals, RMSE, T-values. Those are available in the model summary. So when you are not sure if something is available or not, my recommendation is to visit documentation and then see what's available over there. Okay. So that was a very brief introduction to how to solve a linear regression problem using PySpark. Now, let's try to add more details, okay? So the first thing that bothers me is that we're training the model with the entire data set, which is not good, right? So you probably want to split the data set into a training set and a test set so that you can validate your model more rigorously, okay? Of course, this linear regression model has been trained on the entire data set, so the RMSE here is kind of biased, right? So for that, one trick that you can apply is to split the data frame into two, one for training and one for testing. And luckily, Spark already comes with that feature because it's very common to split the data set, right? So in the data frame, you can call .random split, okay? And then just specify how you want to split. So 0.7 and 0.3, that's kind of, standard practice for many data analysis problems, right? So usually people split it into 70% training set and a 30% test set. There's no scientific reason why people ended up using this most frequently. And of course, depending on the data set that you have, you may want to have a different proportion. But I think 70%, 30% is kind of a standard practice that works with many situations. So after the split, we can simply, so as a result of df_random split, you basically have a randomly splitted training data set and the test data set. So what you're going to do is then to, instead of fitting the linear regression model and the entire data set, you can train the model on the training data set only. And by doing that, maybe the coefficients will be slightly different because we have now a subset of the entire data set. So you can see that the values have changed, a little bit. Same thing with the intercept. That's actually a lot of change. Interesting. Well, we'll see. And after the training is done, then you can, use that linear regression model to evaluate, okay, the test data set. And as a result of that evaluation, you're going to have a data frame that contains the predicted labels. Okay. So that's essentially how you could, train a model and then use that model for making predictions. So predicted is another data frame. So you can obviously just, I'm sorry, this is actually a linear regression summary, not the data frame. You can convert this into a data frame by, I forgot actually. Predicted.predictions, and that must be a data frame, yes. So by doing this, you can see the prediction, and it already compares the prediction with the ground truth value. So features column is the feature vector, quality column is the ground truth response variable, and then the prediction is the result of prediction, and it looks pretty accurate, right? So the actual quality value was 7 in the ground truth data set, and the model prediction was 6.7. Same thing for the second one, where the ground truth was 7 and the prediction was 6.3, and so on and so forth. Okay, so you can see that the linear regression model works actually quite okay. I mean, I can see some rows that the prediction result is a little bit far off, but in general, it seems like they're doing all right. So that's basically how the linear regression model works in Spark. Now I'm going to go a little deeper into what we've just seen. So in fact, the whole process, okay, to summarize again, the whole process is actually quite simple. You first need to create a Spark session. And what you're going to do is to create a data frame by reading the CSV file. And after that, you just use a vector assembler to create a feature vector and then apply a linear regression. That's it. So it's actually quite simple in terms of usage. However, I want to explain to you a very important concept, what is called a transformer and estimators. So, transformer and estimator. So in fact, Spark is basically a set of transformers and estimators, okay? And knowing these concepts is actually very important for you to understand the other, Spark features, and then apply, pick up different machine learning methods and things like that. Knowing this very notion is quite important, because that's kind of the underlying philosophy of how Spark functions are designed. So in a nutshell, transformer is an object in Spark that converts a data frame into another data frame. So in some sense, I mean, literally, it converts one data frame into another data frame by, for example, aggregating 2 columns and then generating a new column, okay? Or by, like what we just did, creating, by combining multiple columns and then generating a new column that has a vector representation of all the columns. So those kind of things are called a transformer, okay? Another common example of transformer is also a machine learning model that is trained. So for example, the linear regression model here, okay, LR_model, is a transformer in a sense that you can use to transform a test data set to produce a data frame that contains a new column that's called a prediction. Okay, so that's the definition of a transformer. An estimator is a different concept. It takes in data frame as an input. But what it does is to configure some internal parameters. And this actually abstracts the notion of training process of a machine learning model. So if you think about it, a linear regression algorithm here takes in a data frame, and then it configures the internal model parameters, namely the coefficients and the intercept, right? So this one over here, okay, not the model, but LR itself can be considered as an estimator, okay? And usually the output of an estimator is a transformer, okay? So to be more precise, the output of an estimator, the estimator takes in a data frame and then spits out a transformer with some internal parameters configured from the input data frame. Okay, so those are the two concepts that are critical in understanding PySpark. I mean, understanding Spark, not necessarily Python version of it, but the entire Spark ecosystem. Okay, so entire Spark machine learning library and other modules in Spark builds upon these two concepts, transformer and estimator. Okay, so with that, let's scroll up a little bit and then go over the process. Okay, so we created a new data frame by reading a CSV file. So here it's just creating a new data frame. Now, if you look at this process over here, okay, I think I already mentioned, but the vector assembler is a transformer. So this assembler object here is a transformer which transforms a data frame and then returns a new data frame. And this particular transformation defined by vector assembler is an operation of creating a new column called the features by combining these columns to generate a feature vector. So it's a transformer. Okay. I'm scrolling down a little bit more, and here's a linear regression problem. So again, like I mentioned, here we're seeing an estimator whose role is to produce a transformer. Okay, so LR is an estimator whose role is to produce a transformer by fitting it to a data frame. And this estimator is going to evaluate the model parameters, okay, from the data frame that is provided as an input. And then it produces a transformer that contains the internal model parameters, W and B, okay, which can then be used to transform a data frame into a new data frame. Does that make sense? So without explicitly saying, transformer and estimators, in the above exercise, we actually, use the transformers and the estimators, okay? Knowing that is important because then it becomes easier to understand the syntax of Spark, okay? So for example, you may have wondered, why the hell do I need to create this vector assembler object and then do the transformation? Can we not just throw everything into this vector assembler object and then, have a data frame, right? Why would you require a user to write 2 lines as opposed to just a single line, right? It could be just a single function. Same thing for the linear regression problem. Why do we need to create this linear regression object and then do the fitting? Can we not just, apply this directly to the data frame and then train a linear regression model? That's because Spark relies on this quite strictly divided roles of transformers and estimators. The reason is mainly because of the optimization of the process, okay? So by dividing machine learning tasks into transformers and estimators, you can actually optimize the process of, producing new columns and then training a machine learning model to a certain level. Especially the notion of transformers and estimators kind of nicely aligns with the concept of MapReduce. So when we first introduced Hadoop MapReduce, we talked about mappers and reducers. Remember that? So mappers were basically a set of functions that can distribute a machine learning task into multiple slave nodes. And then, the slave nodes are going to compute a local, result, and then we'll send it back to, the master node. And then the master node would, aggregate everything, which is the role of the reducer. So it is sort of like that. I mean, it's not exactly the same as mappers and reducers, but it is sort of like that. And, compared to the mapper reducer strategy, Spark tends to be, much faster than MapReduce. And that actually builds upon this transformer and estimator architecture rather than MapReduce. Okay. So of course, if we go into that level of detail, I think a lot of people will, give up on this course. So I don't want to, go into that level of detail. But these two are, one thing to remember is these two are the core notions in Spark machine learning library. Now, with that being said, let's now try to make the problem a little more complicated. And what I'm going to do is actually to, so we just use the red wine data set, and I'm actually going to download a white wine data set as well, and then make the problem a little more sophisticated, okay, by introducing the wine type variable. So in order to do that, I'm gonna cheat a little bit. So here we already have a code for reading the red wine quality. So I'm gonna just copy and paste over here, and then to make it specific, I'm gonna name the first data frame as df_red, and then I'm going to duplicate the same line, but we'll change wine quality red into wine quality white. And then same thing, it's going to become df_white. Okay. So as a result of that, we now have two data frames, one for one for red wines and one for white wines. What I'm going to do then is to join them together, okay, and then form a single unified data set. But before that, after merging them, there's no column that indicates what kind of wine it is, right? So we will have to actually create a new column, and the command already, df_red.with column. And then I'm going to create a new column called type. And then what I want to do is to fill that with a string red, okay? And oops, why did I execute this? And in order to do that, you actually need to apply a simple trick where you're going to need PySpark SQL.functions. We saw this library before, and then import a literal. So this is to fill the column with the same value. Okay, lit. What lit does is to fill a column with the same value. So what I'm going to do next is I'm going to do the same thing on the white wine data frame. Okay, so df white is going to have another column called type. But for this time, instead of red, we're going to fill in with a string that says white. And just to show you how things look like after adding those, I'm going to display the first three rows from each of those data frames. So the majority of the columns are the same, except that now we have added a new column called type. And that's the one that we can use to differentiate different wines in terms of their color. So after that's done, the later process is something that we've learned already. So df_red.union allows you to just merge the two tables. So it will append df white right after the rows of df red, and then it'll create a new data frame called df. So of course, if I show the first three rows are going to be from the red wine data set. So you're not going to see anything different. But for example, when I do df.where df type equals to white, then you're going to see the rows that contains the white wine data. Okay. So that was how we could combine them. Now, the thing is, the game plan from now is, okay, we combine the red wine data set and the white wine data set just to artificially create this new column called a type. Now, what I'm going to do is I want to add this type variable into my set of regressors. So previously we used alcohol content, sulfates, pH level, density, sulfur dioxide level, and so on and so forth as a regressor to predict quality. Okay, I want to add to those set of regressors a new variable called type to, in a hope that maybe, I can predict the quality better. Okay, so in this scenario, what I would then like to do is to vectorize these columns plus the type column, right? That's what we did previously. So if you remember, we had this vector assembler thing, and then we assembled the columns. So you may just go ahead and type vector assembler, and then input columns is defined as df.columns all the way to -2 plus type, right? That's a full set of variables, and then output call is features, right? So you may just be tempted to do this. But now the problem is, okay, we have a new column that contains a non-numerical values, okay? So for most of the other columns, I mean, for all the other columns, we had numerical values. So we didn't have to worry about converting them into numerics. But here we have a string variable, and by default, there's no way to input directly a string variable into a linear regression model. So you will not be able to actually assemble a vector if one of your columns contains a string variable. So before this vector assembly transformation, you want to have a transformer that converts a string data type column into a numerical index. So for example, I want the index to be 0 if it is a red wine, and I want the index to be 1 if it is a white wine. So I need that kind of transformation. So that's the role of a transformer. And for that, PySpark has a transformer called a string indexer for that precise reason. So PySpark.ml.feature is usually where you can find those useful transformers. For example, vector assembler is part of this PySpark.ml.feature module. So string indexer also lives in that same module. Okay. Now, what we're going to do is then we're going to define a string indexer, which is, and usually the transformers are, of the same pattern. So you just need to define an input column. Okay. In this case, you can specify only one column. So there's no plural here. And the input column, so the one that is being transformed, is the column type. And then as a result of that, I'm going to create a new column called type ID. Okay. So this is basically the way that you can define a transformer usually. Okay. Now, what you need to do next is then to indexer.transform df, right? And one way to see if something is a transformer or estimator is by looking at the function. So transformers always come with a function called transform, and the estimator comes with a function called fit. So you would assume that the indexer is a transformer, so that indexer.transform data frame is going to convert a data frame into another. Okay, but there's one problem. Okay, there's no universally applicable transformation from a string typed column into numeric type. So what I mean by that is, okay, for this particular case, we have the rows with only two cases, either red or white. But you can imagine a different type of data set where the categories are a lot larger than just red and white, right? So in fact, there's got to be some process to go over the data frame and then figure out how many number of categories are needed and figure out which class should be mapped to which index. So if you think carefully, string indexer is not merely just a transformer. It is, in fact, an estimator. So what you need to do is, in fact, you need to fit the data frame to create a transformer that can convert a data frame into another data frame. And what this estimator does is basically to count the number of classes, count how many unique classes are there, and figure out the rules in terms of how we're going to map different classes. And that's the role of this estimator. So if you think carefully, you will realize string indexer is actually an estimator as opposed to a transformer. And like many other estimators, the output of an estimator is a transformer. So what you can do next is then to use the transformer to transform a data frame to produce an indexed column type. So let me try this and see what the result look like. Maybe I can print only 3. So now you can see that at the end, there's a new column that's been added as a type ID, okay? So it seems like Spark somehow decided to go with 1 for red wines. And then, let's see. Sorry. And then for white wines, the index type ID is 0, okay? So that's what this string indexer does. So remember, when I said the notion of transformer and estimator is important, is because that's the key to understand the other features in Spark machine learning library. So basically almost everything is written in that kind of a principle. So you know, almost everything is going to be either estimator or a transformer. And once you understand that, the syntax of Spark ML is going to become quite trivial, right? But if you didn't understand what the transformers are and what the estimators are, then, right, understanding the syntax is going to be a little tricky, because you may say, you know, for vector assembler, which, you know, in fact is within the same, you know, PySpark.ml.feature module, for that one, I didn't have to fit anything and I could just transform it directly, versus for this one, which is a sibling of vector assembler within the same module, all of a sudden we have a different syntax. And you may wonder what the heck, right? But once you understand the roles of transformer and the estimators, the syntax is going to become much clearer, okay? So that's all I got for today. And then on Thursday, we're going to continue talking about the estimators and transformers. And eventually we want to get to the discussion of pipeline. So pipeline is a certain layout of transformers and estimators, which can give you an optimal performance in terms of processing the data and preparing the data, and then finally producing, you know, something that you can feed into a machine learning model. So Spark provides an optimized way of doing all that. So that's going to be our topic on Thursday. And after that, we're going to move towards distance and similarity topic, which is going to be the next module. So thank you very much, everyone, and I'll see you on Thursday.